Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. So first of all, welcome to my class. So as you can see, today's topic is the derivation of the equivalent circuit diagram of single phase induction motor. So in this chapter, previously we have done the constructional part, then we have done the what are the different types of what are the different methods we have, theory we have regarding the working principle, that is a double field revolving theory. We have the cross field theory. So there are different types of theories are there. So now the today's presentation is about the considering the double field revolving theory, how we can derive the equivalent circuit diagram of this single phase induction motor. So the equivalent circuit of a single phase induction motor can be obtained by two methods, namely as the double revolving field theory and cross field theory. Firstly, the equivalent circuit is developed on the basis of double revolving field theory when only its main winding is excited. And we have to remember that when only the main winding is excited, so and the motor is at standstill condition, then it is acting as a transformer. So considering the case when the rotor is at stationary and only the main winding is excited, the single phase induction motor is acting as single phase transformer with its secondary short circuited. The equivalent circuit diagram of the single phase motor with only its main winding excited is shown below. So as we can see over there, follow my pointer, that is this Vm is the supply voltage, and due to that current is flowing, that is Im. And this when this Im current is flowing, so in the stator main winding, so there we can consider that main winding resistance is R1m, main winding reactance is R1 X1m, and there is a Xm, that is the magnetizing reaction, X2 bar and R2 bar, and E1 is the generated EMF. So let us see what does those means. So R1m is the resistance of the main stator winding. X1m is the leakage reactance of the main stator winding. Xm is the magnetizing reactance. R2 bar is the standstill rotor resistance referred to the main winding. X2 bar is the standstill rotor leakage reactance referred to the main stator winding. Vm is the applied voltage, Im is the main winding current. Here the core loss of the system, that is the in the previously when we have derived the equivalent circuit diagram in case of transformer, also in case of the single phase induction motor, exactly the previous presentation we have derived the equivalent circuit diagram. So there we have seen that there is a shunt branch, there we have a R0, there is a X0, but in this case we are not considering that. Why we are not considering? We are considering that is lumped with some other losses. So here it is written that the core loss will be assumed to be lumped with the mechanical and stray losses as a part of the rotational losses of the rotor. The pulsating air gap flux in the motor at the standstill is resolved into two equal and opposite fluxes with the motor. The standstill impedance of each of the rotor referred to the stator winding is given as R2 bar by 2 R2 bar by 2 plus j x2 bar by 2. So this is the referred value that we can consider over here. The equivalent circuit of a single phase winding induction motor, the standstill rotor is shown below. So the forward and the backward flux induces a voltage EMF and EMB respectively in the main winding, stator winding, and EM is the resultant induced voltage in the main winding. So as the double revolving field theory concept is concerned, there we are thinking that whatever we are thinking that there are two fluxes are acting. So and they both have the opposite direction. So one flux we are considering, that is the forward flux, and second one is the backward flux, and due to that we are considering there is a torque of forward torque and there is a backward torque. Like this way, here we are considering that the whatever induced EMF is induced over here, that has two components. One is the forward path EMF and there is a backward path EMF. Okay, so that EMF is actually as per the concept of double revolving field theory. So now at the standstill condition, that means when it is not rotating, we can consider that why this concept is appearing, double revolving field theory. So as per the concept is concerned, that means due to this phenomenon, there is a torque is acting in the, say in the left hand side there is a torque acting, and there is the right hand side there is a torque acting. Both has same magnitude, only they are opposite in phase. So that means what happened, the resultant will be 0. That means the resultant 0 means there will be no net torque is producing over the rotor. So that means the rotor is not rotating. That means the rotor is at standstill condition. And if it is at standstill condition and rotor, then can we say that EMF is equal to EMB? Yes, we can say. Why we can say? That means we can say that forward path voltage and backward path voltage both are same. Otherwise, if any one of them is higher, then it will rotate in that particular torque direction. Okay, so as it is not rotating, as it is at the standstill condition, so we can say that yes, it is they have the same value. Okay, so now we are going to derive the equivalent circuit diagram considering the concept of forward rotor and the backward rotor. Now with the help of auxiliary winding, the motor is started. We know as the motor attains its normal speed, the auxiliary winding is removed. The effective rotor resistance of an induction motor depends upon the slip of the rotor. Okay, so as we have discussed in the previous presentation also, that the resistance, effective resistance, rotor resistance is depending upon the slip of the rotor. So let us see what is the equivalent circuit diagram. So follow my pointer very carefully. This portion is the main important portion of this particular presentation. So here we are thinking of that this is the VM supply voltage. So this is the stator resistance and this is the stator leakage reactance. This is the main winding current flowing, and as in the previous diagram, see, try to find out the similarities. So there are also those components, and here also there is xm and x2 and the x2 bar and r2 bar. So here also we have those components also. So here also we have xm, here also we have the x2 bar, and here also we have the r2 bar. But here, as per the double revolving field theory concept is concerned, we have divided that reactance value, that resistance value, so those values into two parts. So one part is discussing about telling us about the forward rotor, forward EMF path, and the rest amount, the rest half is telling us the backward path. So as we can see in this particular diagram, so follow my pointer very carefully. So there is a dotted line. So above this dotted line is the forward path rotor, and below the dotted line there is a backward rotor. So we are dividing the reactance, resistance, all values into two sections. So that's why this xm is divided by 2. So it is xm by 2. So in the forward path we have used this xm by 2. At the same time, in the backward path also we have used this xm by 2. Now here the other components, what are the components? That is the standstill rotor if referred to the main winding. So rotor resistance and the rotor reactance, that is the R2 bar and X2 bar. So both are again divided by half. So x2 bar by 2 and r2 bar by 2. Here in the backward path also x2 bar by 2 and x2 R2 bar by 2. So we can say that ZF means the total impedance in the forward path, and ZB means the total impedance in the backward path. So here one thing we have to change over there. In the above diagram, the air gap portion is split into two parts. Yes, we have split it. The first part shows us the effect of forward rotating flux, and the second part shows us the effect of the backward rotating flux. The effect rotor resistance with respect to the forward rotating flux is R2 by 2s, and with respect to the backward rotating flux, it is R2 by 2 into 2 minus s. When both forward and backward slips are taken into account, the equivalent circuit shown below is formed. This condition, the motor is running on the main winding only. So that means, so this is the here, see what is the change. So this is the here, follow my pointer very carefully. So here see R2 by R2 bar by 2, here is R2 by 2, X2 by 2. So but when we are considering this we are included those slip components over here. So what are the slip components we have come in the forward path? We have included, instead of R2 bar by 2, we have written that R2 bar by 2s, because this rotor resistance is depending upon the slip. So when it is at the running condition, we have to consider this one, correct? So at the same time, when we are considering the backward path, the backward path has slip of 2 minus s, so we have to include over there. So follow my pointer, this is the R2 bar by 2 into 2 minus s. So this is the this way we can just change the rotor resistance when we are considering the slip. When we are considering the slip, when we are taking into account the it is the induction motor is at the running condition. The rotor impedance representing the effect of the forward field referred to the winding M is given by the impedance shown below. Okay, so this R2 bar by 2s plus j half x2 bar parallel with j x2m. So that means it is telling that this whole component, follow my pointer, so x2 bar by 2 and R2 bar by 2s, this whole component is parallel with this x2 xm by 2. Okay, so the rotor impedance of the single phase induction motor representing the effect of backward field referred to the stator winding M is given by an impedance shown below. Okay, so this is the backward impedance that is parallel with this magnetizing reactance. So therefore we can say that forward path impedance is given by the parallel of this two, and backward path impedance given by parallel of this two. Once again I am repeating, it is very important to understand. So as the diagram is concerned, so follow my pointer, this impedance, so R plus X impedance is parallel with this one. Here in the backward path also, these two impedances, the resistance and reactance combining the impedance, that impedance is parallel with this XM2. Okay, so that's why there is the forward path impedance that is given by R2 bar by 2s plus j x2 bar by 2 into j xm by 2 by the summation of all. What is the summation? R2 bar by 2s plus j x2 bar by 2 plus j xm by 2. So like that way we can find out the impedance of that backward path. That backward path impedance also given by 2 R2 bar by 2 into 2 minus s plus j half j x2 bar by 2 into j xm by 2 by summation of all the components, that is R2 bar by 2 into 2 minus s plus j x2 bar by 2 plus j xm by 2. The simplified, so we can say that if we combine, that means here for if we combining that 3 in a single one, and if we combine that 3 series parallel combination, we make a single impedance, then can we simplify the diagram? Yes, we can simplify. So if we simplify, the simplified version of this diagram will be like this. What we can see over here, what is there in this diagram? So there is a RF, forward resistance, there is a XF, forward reactance, so there is a RB, the forward resistance, so there is a XB, the forward reactance that we have. So here in this particular, so what is this total current? So the total current is given by obviously Ohm's law, the voltage by the total impedance of the circuit. So what is the total impedance of the circuit? That is given by the supply voltage by Z1M. So what is the Z1M? See here, there is a stator resistance as the leakage reactance of the stator side, that is R1M and X1M. So that is combining that Z1M, okay, plus the forward path impedance plus the backward path impedance. So combining that three, we will get the total impedance of the circuit, and after that we can find out the main current flow through the stator of the circuit. Okay, so this is all for today. So I think now you are able to understand that using the concept of double revolving field theory, how we can draw the equivalent circuit diagram, and then after drawing, how we can include the, when at the running condition, how we can include the slip components. After inclusion of the slip component, how we can make the series parallel combination of this resistance and reactance. After doing that, how we can make the simplification, and how we can find out the simple current of that equivalent circuit by using the Ohm's law. So this is all for today. Okay, thank you.